Hey guys, this is Alan with Bothell STEM Coach, and today I wanted to talk about an algebra topic. And the formal term for this is binomial expansion. Okay. Now, when I was learning this in grade school, and I'll try not to date myself, we used the technique called FOIL. Now, FOIL is a great technique, but it's a rote technique. It is a way you do this by following a specific set of rules and patterns. That's how a lot of math was taught to me, is through rote memorization, and you just drill until you get it. Now, that works for some people. It doesn't work for everybody, and it doesn't make a lot of sense. And it's the other downside with rote memorization is you may not remember it later if all you did was just drill and memorize it. After like 10 or 15 years, you may not even remember what the heck you were doing. So binomial expansion is talking about doing things like this. Say I have x plus 1 times x plus 2, for example. Okay, the FOIL technique is to say, well, the FOIL stands for different things. I do first, then outer, then inner or inside, and last. Okay, and to expand this out, you do first times first, which would be x times x is x squared. You do outer, which is plus 2x. You do the inner, which is the 1 and the x. And then you plus 2, and you get this. Okay, so I'm very comfortable with this. This is what I learned and what I'm good at. But it doesn't make a lot of sense. You're sort of like, okay, why am I doing first? There's several problems doing a rote. Is why am I doing these four, first of all, and then also what happens if it becomes like something more complicated? How do I do something like this? What's first? What's outer? What's inner? Okay. So this isn't a great way to introduce the topic necessarily. I mean, for some people, it's fine. They're good at pattern recognition, like me, and they just say, this is the rule, this is what I'm going to follow, and done. But a lot of people don't, and they find they learned at some point that if they're not good at the rote, that they're just not good at math. So I want to talk about the different ways we're going to look at binomial expansion. One is a graphical method. This is really good for visual learners, people who understand conceptually, like visually what's happening. The way you want to think of it for this case is that the product of two numbers is a bit like an area, right? When I multiply two numbers, I can think of it as a rectangle, and I'm finding the area of such a rectangle. Okay, so let's take a look at a rectangle and say the rectangle has length x plus 1 and x plus 2. The area, which would be the product of x plus 1 times x plus 2, would be what we're looking for. And if I can think about it for a minute and I smartly divide my rectangle into parts where I would say, well, let's say the length of this part is 1 and the length of this part is x. That makes the length of the whole thing x plus 1. And I'm going to do the same over here where I say this length is 2, this length is also x, and hence this whole length is x plus 2. And then if I think about the areas of so you see this division has created 4 subrectangles. So the area of the larger rectangle is simply the sum of the areas of the little rectangle. Well, if I think about each rectangle or each shape here, I could say, well, the area of this part is x squared because it has length x by x. The area of this part is x here and 1 here, so it would be 1 times x. The area here is 2 length 2 here and length x here, 2x. And then the area of this part, this is a 1 by 2, right? So that makes it 2. And if I add up all the area, I get x squared plus 1x plus 2x, which is 3x plus 2, which is the same as what I had over here. Right? So this is a graphical representation of how the binomial expansion works and why each of the terms comes into play, where the 1x comes from, where the 2x comes from. And it's also extendable. Say I wanted to do this. Times x plus 3. Okay? So this is not a binomial. I mean, this is a kind of a binomial expansion. I got 3 terms in here. So this is I can't use FOIL anymore, or not in a not in a traditional way. But if I think of it graphically, then I can do this. I can say, well, this side is the x plus 3. So I'm going to make this side 3 and this side x. And then I have an x squared plus x plus 1, and I just think of it as I've divided it into 3 sections. This length is 1, this length is x, and this length is x squared. And now I have 6 segments, 6 rectangles. Imagine that these are straight lines, and I'm an amazing drawer. So let's do each component area. This is a 3 by 1, so this is 3. This is an x. This is an x squared. This is an x by an x squared, x cubed. This is an x times 3, 3x. This is x squared times 3, 3x squared. So the product of this would be the sum, would be which the area of the larger rectangle, which would be the area of each of the subrectangles. I'd have an x cubed. How many x squareds do I have? I have a 3x squared plus x squared. That's a 4x squared. I have a 3x plus an x. That's a 4x. And I have a plus 3. Okay, so this is the graphical method. This is very different. I never learned this method when I was learning algebra, and I took a lot of advanced algebra classes, and I was ahead and everything, and I did very well in those classes, but I never learned this method. So I think this is a pretty strong method and an excellent way to sort of conceptually understand what we're multiplying and where all the pieces come from, okay, if you're a visual person. The other way I want to do it is analytically. Or algebraically. Okay. And this method is something that I didn't realize until later that was actually true, what was happening. Let's do the x plus 1 times x plus 3. Now, there's a property of math that says we're doing distributive property. And the distributive property is that you might have learned this in grade school in math, but you didn't really think about it and had forgotten about it since. But it says this: if I do 3 times 6 plus 5, for example, it's the same as 3 times 6 plus 3 times 5. Okay? And this side is 11 times 3, which is 33. And this is 18 plus 15, which is also 33, right? It means I can distribute the 3 into both the 6 and the 5. The same thing can happen with this expression. And this is a pretty powerful one too. I can say the x plus 1 gets distributed to the x and the 3. So I would say I have x plus 1 times x plus x plus 1 times 3. Okay, I simply did the exact same property. I just distributed to each of those. And then I do the same thing again, except I kind of reverse it. I distribute this way, which you're allowed to do, because order of multiplication doesn't matter. That would be an x squared plus 1x plus 3x plus 3. Or this is x squared plus 4x plus 3. Okay? And so this is a powerful way. You're just using basic distributive rules, and you understand where it comes from. Now, I get why FOIL happens. FOIL is a faster way of doing this, so I don't have to write out all the steps. But this is more natural, at least, and more intuitively for some people who are analytical or very rule-based about mathematics, following using the exact properties that you're allowed to use for math, which is a good thing. So let's look at one of the more complicated ones that we just did. X squared plus x plus 1 times x plus 3. At least let's double check. Did I say x plus 3? X plus 3. And we got this answer before. We should get the same answer, otherwise then we didn't do the math correctly somewhere. Okay, so I'm going to distribute this to the x and the 3. So I have x squared plus x plus 1 times x plus this times the 3, which is x squared plus x plus 1 times 3. And now I'm going to, again, distribute. But distributing can happen to as many terms as there are. It doesn't just happen to 2 terms. Okay? So the x times x squared is x cubed. The x times x is x squared. The x times 1 is x. Plus 3x squared plus 3x plus 3. And if I combine like terms, I have x cubed by itself I have 1x squared here, 3x squared, that's 4x squared. I have an x and a 3x, and that's plus 4x, and I have plus 3. And if you compare to our previous one, previous page, x cubed, 4x squared, 4x plus 3. So that's kind of two ways to think about doing binomial expansion, so to speak. But it's not really. It's really just breaking down very simple property, either graphically or analytically, using the same properties. And I feel like those kinds of things can stick around a lot longer than rote memorization for a lot of people. Like when you really understand why something is the way it is, like you'll understand the reasoning more than you'll understand the acronym or the rote memorization part. Like that's just how I feel. And I feel like that's how math for me has been able to stick around for so long, is that I understand it and thus I internalize it. Like riding a bike, like speaking English, those kinds of things just become natural over time if you really understand and do it a lot. So I hope you enjoyed that video. I hope that helped clarify some of the binomial expansions, and hopefully it'll stick around for you. All right, please leave a comment, like, or subscribe if you thought anything about the video, if you enjoyed the video at all, and I will see you next time.